Good morning, good afternoon, good evening, depending on where you're located. Welcome to this webinar organized by the DFI Sustainability Committee. My name is Gerald Verbeek. I'm the chair of the Sustainability Committee, and I'm with Allnamics in the Netherlands. This webinar is going to deal with energy foundations, but to introduce this a little bit, I would like to point out a couple of housekeeping notes first, and then we'll talk about some of the background. During this webinar, you will be muted. That does not mean that you cannot participate. In the Q&A box that you have, the chat box, you can put in your questions that we will then hopefully answer at the end of this webinar. Tony Amos will be giving the main presentation, and he and I will try to answer all the questions that you may have. As you already heard, this webinar is organized by the Sustainability Committee. And the question for some of you may still mean, what is sustainability and what are we talking about? Because it is one of those words that comes up more and more and more, but what is really sustainability? And the definition that you see on your screen right now was one that was developed quite some years ago by the United Nations, by the Brundtland Commission, that said that sustainability really means development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So what we're doing now should not affect it. The future generations can live on this planet. It's a kind of generic description, and it applies to all kinds of aspects, and that's why the United Nations came up with what they call the Sustainable Development Goals, the SDGs. And you see those 17 SDGs that have been defined on your screen. And they cover really all kinds of aspects of sustainability, many of which have absolutely nothing to do with foundations. So when we're talking within DFI about sustainability, we don't try necessarily to cover every single one of them, but we can focus on certain aspects of those elements. Another good way of figuring out what sustainability is a webinar that was organized, in March of 2022, when we had 4 executives of American companies try to give their take on what it is that sustainability means for their company, and also why it makes sense that we are dealing with sustainability. And as you already saw a moment ago when I clipped too quickly through those slides, here are those 4 different CEOs that were there. Eric Drove with Keller North America, Seth Perlman with Munar, Victor Romero with Macmillan Jacobs, and Sue Frank with TEI Rock Drills. Large companies, small companies, engineering companies, contractors, equipment manufacturers, all 4 of them gave their take on why sustainability really made sense and why we in the deep foundation industry should focus on it. Another way of looking at why it is important for us in the deep foundation industry has to do with the climate action. Climate action, when you look at the way we are dealing with it in the deep foundation industry, can really be illustrated with the carbon calculator. Let me back up one step. If you look at the various aspects of climate action, you see in here the different goals that were identified, and one of which you see in the middle part on the right hand side is that we limit the amount of emissions. Limit, in other words, the carbon footprint of what we're doing. And the carbon footprint really covers every single aspect of the activity. It's the manufacturing of the equipment and the materials that we use. It is bringing those materials to site. It is mobilizing staff to site. It is installing the items into the ground. All different aspects, all that together forms the carbon footprint. And the reason why it is important is that carbon footprint is then expressed in the equivalent tons of carbon dioxide, equivalent of CO2, and the carbon calculator can help you do that stuff. And that is one thing that DFI, together with the EFC, developed some time ago to give you a tool that really helps you develop this carbon footprint. So that's one aspect of sustainability that plays a role in this whole thing. Second aspect there is that you are using the resources smartly, that you are really trying to make optimum use of those resources. And that was emphasized in a conference that was held not too long ago on the foundation decarbonization and reuse. Because obviously, if you reuse the foundation, you don't have to build a new foundation. So therefore, you make better use of the resources. And obviously, you don't create additional emissions. So that's another example where the sustainable aspect of foundations can play a role. We also have within DFI a task force that deals with foundation reuse. And if you're interested in that, let me know or let DFI know. We can help you with that part. But during that same conference, there was also another part on that, and that had to do with renewable energy. One of the examples that was given is not something like this, where when we talk about renewable energy, people often think about wind farms, be it offshore, be it onshore. But the example that was given in that conference was a system like this, where a building was put together, was built or constructed on the side of a canal, and where the water temperature was utilized to come up with the hot water for the shower, the floor heating, and the hot tap, or the hot water in the tap, and all that through a heat pump. And while this had nothing to do with necessarily reuse of foundations, it was an example how you can make a more sustainable use, how you can do things more sustainable. And that brings me then to the topic of today, where we talk about energy foundations. How can we utilize the heat in the soil, or in this case that you see on the screen right now, the heat in the water, to either cool or heat a building, and therefore reduce the amount of energy that you need, be it gas, be it oil, to heat that building. And the center of that is a heat pump. And the person that we've asked to talk about that is Tony Amos. Tony is the chair of the work group now that we have within the Sustainability Committee dealing with energy foundations. And he will give some examples on how energy foundations can really be utilized and how it can really make a big difference. But in order to help you understand this as an audience better what the whole functionality or how this thing works, I've asked Tony first to talk a little bit about the heat pump, so you understand what this central part of an energy foundation really works, and then he'll go into his presentation. So with that, Tony, the floor is all yours.
Thank you very much, Gerald. And yeah, it's kind of been a part of the DFI Energy Foundation Committee for quite some time now. I'm hoping that I can. There we go. So, so I have been part of the Endurant team for the last 15, 20 years, basically designing and building geothermal solutions. It all kind of started for me back in the UK. I came from a drilling background, drilling foundations with Skanska, Verbeek in the UK, and what I ended up was on one project where they were. I'm just going to go back to this particular slide here. They were trying to drill a borehole to provide heating for a hospital, and I kind of felt, well, why can't we put those geothermal loops into the building foundations that I'm drilling? And that's, for me, 20 years ago is kind of where it all kind of started. Fundamentally, what we're looking at is a heat pump, ground source heat pump. A lot of you probably will hear air source heat pumps. The key difference between an air source heat pump and a ground source heat pump is that with the air source heat pump, we're utilizing the air temperature at a moment in time to deliver heating or cooling. So when it gets very, very cold in wintertime, the heat pumps are having to work extremely hard. Similarly, in the summertime, when they were trying to provide cooling, again, the air source heat pump is trying to exchange heat with the air that's already very warm and provide a cooling solution. With a ground source heat pump solution, It all hinges around the second law of thermodynamics, and that is that heat will always move to a colder place. And so the beauty of the ground source heat pump solution that we are talking about today is that the ground that we're drilling foundations into, once you get below 10 feet or so, the ground temperature remains pretty constant year round. And here in New York, we've seen it range from 55 to 60 degrees Fahrenheit. So you can imagine, again, in the summertime, when we're trying to provide a cooling solution to a building, we've got that nice cool ground to provide a cooling solution to. In wintertime, again, we're trying to provide heating, and what we're doing there simply is utilizing the ground temperature at around 55 to 60 degrees to bring in heating to the building. So the loop going into the ground, all we're looking to do there is exchange probably 5 to 10 degrees of sort of cool from the building. So as the loop's going to the ground, what we're looking to do is to bring the fluid in those geothermal loops and increase it by somewhere between 5 and 10 degrees Fahrenheit. That then passes through a refrigeration cycle. It's typical of a refrigerator in everybody's home. So that added heat is then passed through an evaporator. And what happens there is there's a refrigerant in that evaporator that when we warm it up by that 5 or 10 degrees Fahrenheit, it moves it from a liquid state to a boiling state. And then we then compress it. You can see the compression at the top there. And when you compress that gas, when you compress that boiling liquid, you convert it into a gas, which raises the temperature even further. So what we're looking to do is to take that low-grade temperature from the ground and convert it into 120, 130 degrees Fahrenheit in the building, sufficient to provide heating for hot water and heating systems for within a building. In a summertime situation, we're taking the heat out of the building in very much the same way. So the building effectively becomes that ground loop. We're taking the heat out of that building and moving that heat back into the ground. So rather than the loop going out cold and then coming back warmer in the wintertime, the loop goes out warmer than the ground is, and then it's coming back slightly cooler. So it operates in reverse. So these systems will deliver heating and cooling. So it's all about removing the ability to remove boilers, traditional boilers in the basement that we've seen, and maybe rooftop chillers. So you effectively save considerable amount of space within buildings, basically, with a heat pump. And again, just very quickly, the air source heat pump, ground source, if you can deliver whatever the ground temperature is coming from the ground to the building temperature, if you can keep that as narrow as possible, that's when you're going to get the most energy efficient solution. So the air source heat pump in a winter condition, you may have 0 to 10 degrees Fahrenheit, but the ground temperature is at 55 to 60 degrees. So that lift, the heating is much narrower. So you're going to end up with a much more energy efficient solution if you go ground source than if you go an air source heat pump solution. Exactly the same in the winter, in the summertime for cooling. It's probably enough on heat pumps, hopefully. I probably should have shown this slide. So this kind of slide shows how we can bring in the heating from the ground, which is pretty constant year round, in winter scenario on the left, and then on the right hand side, how we are getting rid of heat and delivering cooling to the building in the summertime. Okay, so one of the problems that I've heard many times as well in a city centre site like New York or Chicago or Washington DC or London, what are the solutions for geothermal solutions? And part of what we do as a business here is to get involved as early as possible in the construction process. And look at and offer a feasibility. And when we offer that feasibility, we're going to look at options that are available to us, that we can utilize that heat exchange that I've sort of outlined previously with a heat pump. But we can use things like sewage water for that instead of the ground loops. Or we can look at other water sources, and those other water sources might be sort of railway stations, subterranean railway stations that are constantly pumping out water 24 hours a day, 365 days of the year, to maintain a dry and operational railway station, for instance. We can tap into that water, and I'm going to come on to that in a little bit more, probably in the next slide, actually. And we can tap into that and how we can utilize that water. Again, it's going to be at a constant temperature, similar to the 55 to 60 degree that I mentioned previously. And then there's the hybrid ground source heat pump solution. I call it hybrid because the picture on the left there you see is a commercial building. It had 63 foundations in it, 120 feet each. When we did a quick calculation, we couldn't deliver all the heating and cooling to that building from those foundations. So there are options, and the options are that we can add geothermal boreholes in amongst those foundations if necessary, or we can look at an air source heat pump that helps to deliver that peak cooling situation for the winter and summer time scenarios. So we kind of combine those two solutions together, or we can look at them all together for a solution. So let's just quickly dive into some of the other options. I know we're talking about energy foundations, but I just want to make sure people are very aware of these opportunities. So on this kind of one, we've done a lot of work with NYSERDA here in New York State Energy Research Development Agency. We've done a lot of feasibilities for district energy opportunities, and one of them was some buildings, new residential units, 950 affordable units, and a school in Brooklyn in New York City. And when we calculated the amount of heating and cooling we would need a flow rate of around 4,500 gallons per minute from a sewer pipe or the MTA water scenario. And in our sort of research and due diligence, what we identified was that there was a very large sewer that was running down the high street next to the site. And within that sewer was a range of 19,000 to 51,000 gallons a minute of very nice warm liquid that would enable us to deliver all the heating and cooling to those 950 affordable units and the school. And in reality, that sewage solution would be enough to heat up to 4,000 apartments. Now, the beauty of that system is that we could replicate that along the route of the sewer pipe many times. So it becomes an energy source. The challenges we have for this, the benefits of this is you've got a small location that's then requiring sort of an interception to the sewer rather than drilling lots of boreholes. We can deliver pretty much all the heating and cooling in this situation. So there's minimal schedule impact with this type of solution. The key challenges that we're being faced at the moment is the lack of these types of systems in certainly the US. That said, we have taken a group of government officials up to Washington because there's a really great solution like this that's been operating now for probably 4 or 5 years at the American Geophysical Union building in Washington, DC. And it's heating and cooling the entire building. And you can go down into the car park of that building, and you can see they've got glass screens that you can see all this equipment operating. It's a pretty neat solution. But the DEP are pretty. There's a lot more work to be done to investigate that type of solution. So the next option, and one of the things I've seen a lot in the US since I've been here for the last 6 years, is the go-to solution is pretty much, okay, we've got to drill boreholes. And quite clearly that there are lots of other options available to us that need to be explored before we go down this route. And if no other solution is available, then okay, let's drill boreholes in amongst the foundations. The picture on the left, foundations there were not they were too short to be effective. So we lowered 2 drilling rigs into the basement and drilled in amongst the as they were completing the excavation there. And this was a pretty neat job. We did one of the things that we see a lot is drillers driving onto site and creating an almighty mess. The picture on the left, we created a nice concrete surface for these guys to work from. Productivity increased dramatically, and the guys were able to drill 2 boreholes a day. And I would suggest that there was no impact on the construction schedule on this particular project. As soon as those boreholes, you can see the machines. This was in a basement. You can see the machines excavating away. They're creating the rat slab behind them, and then our drill rigs are then drilling in. I think it's probably 20-30 boreholes down to 500 or 600 feet in this case. And as soon as the next team are coming through, laying the reinforcement on the, as you can see on the right-hand side, we're doing flow test, pressure testing, and headering up straight through the basement slab. So again, minimal impact on the construction schedule. And that's kind of one of the key things about being involved in these kind of projects, is that collaboration, not only with the consultants involved with the project, but certainly the team that's building the project as well, getting everybody engaged with what's going on. So from a geothermal sense, I mean, we've alluded to two key solutions so far, but geothermal loops can be installed in lakes. We can put them into we can lay them horizontally under sports pitches. We've done a lot of schools for that kind of solution. Drill boreholes, I've already mentioned that. We can extract water from MTA. We can extract water from an aquifer. We can remove heat, add heat to that water, and then put it back in the ground. That's called an open loop solution. But primarily, we're going to be talking about energy foundations here. And I've probably done almost 70 projects in the UK and the US. And when you're drilling foundations for a building that's probably 60, 70 feet plus, you've got a great solution here that's going to give you a significant amount of heating and cooling to this building that's going to help tick the carbon reduction box. And the beauty of energy foundations is that, again, the collaboration, the coordination between key parties. Of the 70 projects that I've been involved with, I would say that the schedule impact has been absolutely minimal. We managed to coordinate our activities alongside the piling contractors and the guys forming the basement itself. So, oops, too far, too quickly. So, interesting, far too. So, what is an energy foundation? So, again, that early stage discussion with the team, structural engineers, the geotechnical guys designing the basement and foundations. All that we as a team are looking to do is to utilize the structural capability of the foundations. We're not looking to change it in any shape or form. There may be a discussion about how we get the reinforcement, the full depth of the pile. But fundamentally, all we're looking to do is place a geothermal loop from the pile trim level all the way down to probably a foot off the toe of the pile. And as you can see in these 3 pictures here, a lot of the activity is done off of the critical path. And this was one of the largest projects I was involved with in the UK. With my cementation hat on, we had 60-meter deep foundations here, and we had pretty large. It was top-down construction, and what you see in the top right there is the 3-meter diameter cage, and we ended up putting 7 geothermal loops in that. Now, these guys were only able to construct 1 pile a day anyway, so and again, a lot of discussion and planning went into how we would install those loops. all 2 or 3 lower cages were installed into the foundation to begin with. And then the picture on the right is the top section with the loops pre-attached, all bundled together. Those loops were threaded through the lower cages. And then the picture on the bottom is the cage, once it was spliced together, being lifted out, and we were just pulling the geothermal loops to the outer face and tying them to the reinforcement cage. Process that probably added 15 minutes to the construction process there. The guys couldn't construct any more than 1 pile a day per rig on that particular site anyway. So, you know, they were finishing by 4 o'clock each day anyway. So again, I would suggest there was very little added impact on this construction program. So this is an interesting project, and I'm going to talk about energy modeling, which is a crucial component of what we do. So this particular project was completed in 2010. I know there's a team of guys in the basement at the moment there, having gathered an enormous amount of data. And what we found here is actually we can deliver a whole lot more heating and cooling, because the energy model that we were given that told us how this building, the amount of heating and cooling this building was going to need, was way over what was really truly needed. And on this particular project, they're currently removing all the gas-fired boilers, because the energy foundation solution here has the capability to deliver all the heating to this building. And by increasing the amount of heating, it means we can also increase the amount of cooling. Because what we want to do is we treat the ground like a battery. What we take out in heat, we can put back through the cooling process and dump heat back in. So we can play around. We treat the ground rather like a battery. And over probably the last 20 years, I've installed geothermal loops in every type of foundation solution imaginable. And I'm British, so excuse me for using some wrong terminology. It's one of the things, you know, you guys deal in inches, I deal in centimeters and millimeters and things like that. But even terminology, board piles, displacement piles, continuous auger piles, CFA piles, driven cast in situ piles, all have different names. But hopefully the picture tells you and shows you that, you know, every foundation solution is possible. Even precast piles, H-beam, as you can see on the right-hand side there is a geothermal solution for it. And back to 2017, to when I first arrived here, one of the projects I was brought over for was to look at and work with the Google team and oversee the installation of the geothermal loops in 3,000 piles that Malcolm were installing for the Google head office. Now, a lot of preparation of the critical path, as you can see on the left. So no construction impact. There's a little video clip. So again, the piling contractor is carrying on as usual. In this case, he's drilled down 120 feet. And what you see is that geothermal loop attached to that single piece of reinforcement. That's required anyway. And we're just utilizing that piece of reinforcement to install the geothermal loop. And that one pile that's being formed there is one of the piles that it forms the pile cap you see on the right hand side there. So interestingly, so this is 120 foot, and not wanting to give away the secret sauce from Malcolm, but these guys were drilling over 25 piles a day. Now, if we were to drill this site with geothermal boreholes, in most cases, they would have drilled 500 feet of borehole in a day, and that would have been it. So pretty much equivalent to maybe 4 of those energy foundations being installed. The other interesting point about this project here, the site at Google was highly contaminated. So the piling solution, a displacement pile in this case, you can see the amount of spoil that's generated from the process on the left in the video clip. Absolutely minimal amount of soil. So it minimizes the removal of contaminated material off site. Absolutely enormous cost saving. So to drill boreholes, we'd have ended up drilling, we're producing a lot of slurry and material as well. So a lot of added benefits to this type of solution. So on the right-hand side there, one of the things that we do is we do a lot of flow and pressure testing to verify the geothermal loops have been installed without any incident. And you can see the guy doing that. So each pile in this particular case is connected together. And so what you've got on the right-hand side there is the equivalent of almost 500 feet, which would be a typical borehole depth that we see here in the US. In New York State, we're restricted to drilling to 500 feet. If we drill over 500 feet, we then have to go down and get special permits, measure verticality, a lot of added cost. Let's talk about the design developments. I'm going to focus on this one particular project that I've spent the last 2-3 years working on in central Manhattan. So 250,000 foot square commercial office. We were told we had 300 tons of peak cooling. Sorry, my screen just went off. 300 tons of peak cooling and 70 tons of peak heating needed to be delivered. They were going to build a radiance. They were going to install a radiant slab heating and cooling. That in itself is always a great sign, because what it means is you can deliver heating at a much lower temperature than you would to a conventional system. So it doesn't need to be 120 degrees. It can be a lot less than that. So it's more suited. A ground source heat pump solution with this kind of system works really well. So obviously understanding the geotechnics of what the foundations are being drilling in, we've got to try and work out what the conductivity value is. I mentioned the heating and cooling. Those one of the key things that we need. The absolute crown jewel is an energy model. So the mechanical engineering will kind of provide us with an 8,760 hours every year. And for every one of those hours, what we want to know is how much heating and cooling is being called for the building. And that enables us to do quite a lot of iterations and working out what the optimum geothermal system is. At Greenwich, it started off with much 12-inch diameter piles, 360 odd, I think, from memory. The final solution was 24-inch and 36-inch foundation piles cast in place. So we then modeled that 192 U-tubes, thought we could get 3 loops in each of the foundations. And then obviously working out what that looks like in terms of the headering arrangements. So the 3 loops in the foundations look like this. Again, trying to utilize the full depth of the pile as much as possible. The engineer was specifying full length reinforcement anyway, so no additional reinforcement was required. No additional drilling was required in each of these cases. And so we installed 3 geothermal loops within the foundations, as you see here. And then the key is obviously how we feed each of those piles back to the submanifold. And in this case, what we've got here is a west zone and an east zone. So the site is split into 2. And what you can see here is 3 loops are connected in series and then run back to submanifolds. So each of these submanifolds had about 7 or 8 piles connected to them. The beauty of that is if the one of the foundation piles does have a problem at a later date, we can isolate it at this manifold, rather than daisy chaining everything together. If one of them goes down, they all go down. So, during the design process, it's important to understand the kind of long-term resilience for this kind of solution with these kind of solutions. Talking to the architect, where can we house these submanifolds? Where can we site the main manifold? These are key questions that we will answer. And so this is what kind of the manifold looks like. So each of the foundations are running back to something similar to this. And then from here, we've got these pipes run up to the roof to the heat pumps that do all the heating and cooling. So again, understanding the foundation depths, the amount of loop that we've got inside in the ground is crucial. Having the energy model is essential. The graph here on the right hand side is kind of showing us what happens over a 25-30 year period, what we're expecting to see. So we know we've only got 192 loops in this particular project. So that's 3 loops and 63 piles. And the design here is telling us that we can deliver 31% of the cooling to this building and 38% of the heating load. But what's really important is to understand what happens over time. And what you can see here is that this is a cooling dominant building. So we're going to be putting more heat into the ground through the year than taking out of it. So what we're going to see is a gradual increase in the ground temperature. So what's really important to us is once this is installed and becomes operational, we want to monitor this and make sure this doesn't go off the scale. And with a hybrid solution, what it enables us to do is to start to play. We can optimize this output, so we can deliver more heating, and then perhaps we can deliver more cooling as the time goes on. And with the air source heat pump on the roof, we can help regulate this ground loop. So again, it provides that hybrid solution I mentioned at the beginning, enables us to provide a resilient solution that's going to survive for the next 25-30 years. Some of the projects we did in London for Crossrail, the design life there was 150 years. And again, reuse of foundations is increasingly being talked about. There's absolutely no reason why geothermal loops into building foundations couldn't be reused at a later date as part of that process. But what we see here is the output for the project in Manhattan. So we're delivering 40% of the heating, almost 31% of the cooling, and then the remaining heating and cooling is delivered from an air source heat pump, ultimately. So let's have a look at how we built it and what does it look like. So again, working with the foundation contractor now to make sure that we don't impact his construction schedule at all. So we came up with, we provided these loop reelers. So you've got one loop on this reeler over here, and there's 2 loops on this one. So as they lifted the cage into place here, these have been drilled down to 120 feet. And we've got this single piece of reinforcement that's fabricated in 3 sections. So as this cage is being installed, we're simply attaching the geothermal loop to the reinforcement cage. Excuse me. And interestingly, what you see here, some blue cables. So this is all the instrumentation that we installed on this one particular pile to help our control strategy. Going back to that the temperature graph, that's going to enable us to monitor the amount of heating and cooling that we can deliver from this solution. So what you see here is the loop being installed, and probably the biggest impact we had on the piling contractor here was on this spacer plate. We asked him to cut half moons so that as this cage went down, we could slot the geothermal loop quite snugly into that and tie it at that point. And again, minimal impact. Another video clip here, speed it up. You can see the lower cage being installed, geothermal loops being attached at each stage. And then there was a rather long pause while they fitted up the next cage section and then lower that down. And then in this final piece here, we'll see some white sections of pipe being added in, which are in the pile trim zone, the final pile trim zone. And you can see that in this picture on the right at the top here, which is important. And I'll come to that in the next slide. But importantly, the QA/QC, making sure that we've got the loops have been installed without any damage, flow test, pressure test is a crucial part of the process of making sure verification. When you've got 63 piles, you've got to get it right first time. One of the things I was quite impressed with actually, and I realised, is that HDPE, high density polyethylene pipe, which is what the geothermal loops are made of, is pretty bomb-proof, even to this kind of aggressive nature of breaking down the piles. That said, that white tubing you can see here in this little picture down on the left. So as the pile's been excavated, the last thing we want is for the pile, the geothermal loops to be damaged in this zone here. So we provide this little bit of extra protection in that zone, so that we don't damage the loop at this point. If we damage it here, it means we've got to break out further down the pile, which is always a frustrating job for the guy on the jackhammer. And again, so you can see here, next stage, piles being excavated, geothermal loops being exposed. Key next step, flush test, pressure test, running loops back to that sub-manifold location. Again, flush test, pressure test prior to concreting the pile caps in this particular case. And the important part here is that once the pile is tested, a key hold point for proceeding with construction would be to say, okay, is this pressure gauge, has the system held pressure, before they then concrete the next stage. So once the pile caps are formed, it's a case of then running geothermal loops back through to the sub-manifolds, and pretty much we run those through the slabs and foundation works, again working alongside the iron workers, steel fixers in this case. Again, minimal impact on the construction schedule, and then foundation works complete, and what we see here is the kind of where we've run the geothermal loops to in each case. So this is going to be where the sub-manifolds are. So this is a sub-manifold, sub-manifolds. This is one of those typical sub-manifolds looks like at each of those key locations. And again, what you'll see, well, you can't see it in this picture, but again, key, once the foundation contractor's completed his work at this point, there's pressure gauges on each of these geothermal loops. So again, verification, making sure that the loops are constantly under pressure. So if there's a problem, we know about it as soon as possible. So the next phase of works is to then connect up these sub-manifolds and then run them back in what we call reverse return. The important thing with the reverse return is that the distance from the manifold here, the main manifold, to the tip of every single pile is always the same dimension from this manifold. So you then get equal balanced system. So we need to make sure that the piles over here closest are not taking all the kind of heat transfer. And then what we see here is the final sub-manifold installed, and then obviously the next stage is to run up to the roof. But the key next stage here is for us was to flush out and purge the loops of any air. And in that purging process, you can see kind of all the bits and pieces that have come out of the system, even a small stone, concrete piece of aggregate, obviously got into the loops. So quite a lot of time is spent on this stage of works. And then these are the heat pumps being installed on the roof. Now these are pretty exciting units. So these units on the roof of this Greenwich project can operate as either a ground source heat pump or an air source heat pump. So something needs to tell them whether to operate in ground source or air source heat pump mode. So as I said in one of the slides, you could see these blue cables being installed. So Geo Instruments helped us put some vibrating wire strain gauges and temperature sensors into one of the 24-inch pile 4A here, and one of the 36-inch piles in pile 10 here. These two have geothermal loops in, and we also put instrumentation in this pile in the corner over here, which was a 12-inch diameter pile, but it doesn't have any geothermal loops. And you see that we've got instrumentation spaced out through the depth of the pile, and that's all running back to an instrumentation panel in the next to the main manifold. One of the important things is to understand the conductivity value of the ground and resistivity, because they're key design parameters that are used in the geothermal design. And so running a test in a foundation itself, probably it takes a little bit longer than a conventional borehole. So on this particular case, we ran the system for probably 114 hours. So what's that? 4 or 5 days. But what it gives is the system is running without adding any heat to the system. So what it does is it gives us this interesting temperature profile of the ground. And interestingly, on this Manhattan site, typically we would have designed to a temperature around 55 to 60 degrees in New York City. But what we found here is what's known as the urban island heat effect. And what we've got here is a temperature of almost 70 degrees. And interestingly, what you see is how what you see with most piles, it's warmer at the surface, and then it will gradually, as you go further down into the ground, it will probably head back down to the kind of 60 degrees temperature that we expected. What's useful here is in setting up and starting the system, what we're going to be able to do here is deliver a whole lot more heating to this system than we originally believed we could do. And because of the temperature difference between the ground and what's required in the building being so narrow, it's going to be super efficient. The idea here is that over time, through the winter, we can drive down this heating by delivering more heat than the system is designed for. So we can then swing this kind of temperature profile down to where it should have been. So that again, in the cooling, in the summertime season, we've got a nice cooler ground temperature. Again, so it's closer to the temperature that's required in the building. And again, one of the most energy efficient means of delivering heating and cooling. So again, we get a lot of conductivity values, so we can confirm design. What's important is that long-term monitoring. Any geothermal system, it's important that you don't just walk away once it's installed. We want to provide the long-term management and monitoring, because, as I just alluded to, we can start to play around with the ground temperature, so that come the summertime, we've got nice warm ground. We can deliver. Come the summertime, we've got nice cool ground, such that we can deliver a whole lot more cooling than we originally said, and then we can put more heat into the ground, and then in the wintertime we can deliver a lot more heating in a much more energy efficient way. We would call that system optimization. So over the next 24 months, once this system starts to go live, that energy model that we were giving at the beginning, we will be looking back to see, well, is this a true reflection of this building or not? And then working out, okay, how much more can we deliver? What are we actually delivering? What is the actual energy model, and how much are we actually delivering from the ground source heat pump system? And our instrumentation panel here will be able to tell the heat pumps on the roof, you can have heating or you can have cooling. We've got, it'll be sending the signal, and there's an algorithm in the controls on the rooftop equipment, so that there are times of the year where perhaps the air temperature is more energy efficient to use for cooling or heating than maybe the ground. So an algorithm within the control system will then send a signal to the heat pumps to operate in air source heat pump mode. And then as the temperature increases during the day or decreases, then the ground source heat pump system will become more energy efficient. So it'll switch to the ground source heat pump system. So it's about providing long-term management and making sure the ground isn't overheating or overcooling over time. And just final thought here, every time I get on a cab to the airport and see lots of piling rigs, I kind of feel there's an opportunity missed to provide a heating and cooling solution to a building, a low carbon heating and cooling solution. There's a lot of work going on at JFK Airport. LaGuardia, and Newark Airport. I know the foundations there are very deep. This would make an excellent opportunity to use energy foundations, deliver that low carbon energy solution. So that's me done. Hopefully you kind of haven't lost anybody. Back to you, Gerald.
Well, not back to me. We're now going to hopefully clarify some points, answer some questions. But first of all, let me start with a question that I have, Tony, and that is, we talk about an energy foundation. And we of course, as DFI, we know about the deep foundation. Are there consequences to the foundation size itself when you make a foundation into an energy foundation? Is there a concern that because of the loops that you put in there, that there would be quality issues in the foundation? How does the geotechnical foundation part get affected by make it an energy foundation?
Yeah, it's a really good question. And going back 20 years now, frighteningly, 20 years. This was a big question that we were faced with. And many geotechnical consultants said, well, how can you assure me you're not going to freeze the ground, and things like that. And I was very lucky. I was working with Skanska at the time when we were trying to raise the profile of energy foundations. We were very, we had a Duncan Nicholson from Arups was a big advocate of energy foundations, and together, we did quite a lot of research. We combined forces with Cambridge University, and we got the opportunity to do a test pilot at Lambeth College. And again, 2000, and I'm trying to think of the year 2005. So we had a test pile, a Domino 5 type test pile. We instrumented the test pile itself. We instrumented 2 anchor piles. We put geothermal loops into the test pile. Cambridge University put fiber optics in the piles. They put vibrating wire strain gauges in. And there are probably 6 or 7, if not 8, papers that were written on the back of that sort of trial. So firstly, we did the load test, I think for 1200 kilonewtons, load test, working load, tested it up to 1.5 times working load and back down. We then switched the heat pump on. Sorry, we then reloaded the test pile up to its working load, which is 1200 kilonewtons, I think. And then we switched the heat pump on. And then what we tried to do is we were then running the heat pump and circulating fluid at sort of, I think the lowest we could get the temperature down to was -7 degrees Celsius. And we circulated that for about 4 weeks while the load was being maintained on this test. And what we saw was the pile settlement move by probably a millimeter, a very small fraction. Basically what's happening is as you cool something down, it contracts. So we then switched off the heat pump after 4 weeks. We couldn't freeze the ground. So we had some interesting information from the test pile where the loops were, and there were no loops in the in one of the anchor piles. We put a test borehole within a meter, 4 or 5 feet away. So we had a lot of instrumentation about what was happening from around the pile, in the borehole and the anchor pile. And what we could see was the kind of heat effect or the cooling effect from that pile. We then switched after 4 weeks to heating mode. So we went from -7 to the maximum output, which is about 55 degrees Celsius, 120, 130 degrees Fahrenheit, for about 2 weeks. And what we saw was that pile, the additional settlements increased by a millimeter. So again, you get that expansion contraction. And as I said, there's a lot of papers that are out there that kind of substantiate that there was no untoward effects on the foundations. And there's a lot of papers out there that we can provide that support this kind of solution. One of the things that I did realize from doing that kind of test is the misconception that these heat pumps are running at -7 degrees and then switching to 50 degrees. What you see with that energy model is that there's a gradual change over time from a heating cycle to a cooling cycle. So you're not seeing these big shifts in temperature changes on a daily basis. It's a seasonal shift. And again, what's really important to us as a team is to make sure that we're monitoring what's actually going on in the grounds over time and making sure that we're not overheating or overcooling the ground. And we'll try and our designs will not take the fluid temperature below freezing on an energy foundation project.
Right.
So, and I think one of the compressive strength of the concrete was it 0.25 FCU? You have to forgive me because I'm not a foundation designer. But when you work out the space of the space that the geothermal loops take up when you're working out concrete stress, I think that's probably one of the key things to look at.
Yeah.
When you're designing concrete strength.
How much, and when you talk about a typical heat loop, what kind of cross-sectional area is taken away from the pile for the heat loops? In other words, what is the diameter of those heat loops? Because obviously, if you have an end bearing, that's something you need to keep in mind. Well, can you say something about that?
Yeah, sure. So importantly, what we don't want is all the loops coiling up on the bottom of the pile. And we generally try and keep the tip of the loops at least a foot off of the bottom of the pile. And geothermal loops will be 32 millimeters, 40 millimeters, 1 inch, 1.5 inch in diameter. And you have a flow return. So you've got two loops make up a circuit. So at the 561 Greenwich site, you've got 3 loops. So you had six pipes basically, 1.5 inch diameter each.
Okay. When an engineer decides to, or foundation engineer decides that let's start working or thinking about this energy foundation. Obviously, very early on, it's important different individuals get involved in this whole thing to make sure that we get a solution that's there. Could you say something about the type of people that need to have input in this discussion? So far, you've given indications of how it can be applied, but what kind of discussion, which are the parties that need to be talking about this concept of energy foundations to make it a success?
We need to get the developer on board with the solution in the first place. And then being involved with the professional team, the structural engineers, the geotechnical team. And then once the foundation contractor comes on board, it's then making sure that, okay, what's the foundation solution going to be? So what would be what's the geothermal solution going to look like? And certainly for continuous flight auger piles, auger displaced piles, you've got to plunge the geothermal loop through concrete. So it's important at that point to make sure that the piling contractor is confident that he can get his single bar primarily with our geothermal loop attached to it down to the required depth, because there's nothing worse than going to site and then, well, actually we can't get down to the 50 feet mark. Will 40 feet do? You know, I mean, that 10 feet on 100 piles is going to be quite significant in terms of the geothermal design. So it's getting the confidence of the piling contractor, you know, so you need that expertise as part of the process. So it's kind of the architect needs to be involved. Where are you going to house those manifolds, sub-manifolds, things like that as well.
So you talk about a lot of people.
A lot of people.
It really has to be. And then the question is, as you said earlier during your presentation, we don't see that many energy foundations. That means that that large group of people, there's somebody who's saying, nah, let's not do it. Based on your experience, what is the biggest hurdle? Who is creating, is most reluctant to start applying this solution?
Well, yeah, so the problem constantly faced over the last 10, 15 years is the additional cost associated with geothermal solutions. So you get this capex that becomes a problem. I mean, the heat pumps themselves, if you took out gas-fired boilers and rooftop chillers, you could put heat pumps in at the same cost. And the building distribution doesn't change either, as long as it's a hydronic solution. It can be air. But so you then got to put the geothermal loops in the ground. And the beauty of energy foundations is that the solution should be cheaper than a geothermal borehole solution. So it's about that additional cost. So what's really super important is that early discussion, not just talking about CapEx, but also saying, well, look, this is what the OpEx looks like for your traditional approach. This is what the OpEx looks like for the geothermal system. Look at the amount of money that you're going to save per annum. The amount of incentives, tax grants that are now available here in the US are showing that this type of solution, there is no longer a payback on a geothermal solution. The payback is on the traditional approach, and going with that traditional gas-fired boiler, rooftop chiller solution. And under the Inflation Reduction Act, prevailing wage is the primary driver. You should be able to achieve at least a 30% tax grant associated with that particular grant, tax break. In addition to that, if you can demonstrate all the material is coming from the US, it becomes 40, almost 50% of the project value. The other key fact is if you can deliver at least 75% of the building's heating, you can then include within that tax credit, you can also include all the distribution equipment through the building. It really has become a no-brainer of a solution to go geothermal nowadays. Air source heat pumps do not qualify for that grant, that tax credit.
Okay, but even without the tax credit, and when you look at, if you start looking not only at CapEx, because CapEx obviously goes up, but if you include the OpEx and look at the total life cycle cost, that makes sense, especially with potentially rising energy prices. What is a typical, when you say, forget about the grant, but to get people an indication, what would you say on a reasonable project? What kind of payback periods are we talking about?
Well, I mean, here in New York, we're not talking about paybacks anymore. It's cheaper to go a geothermal solution. Prior to the tax credit, the IRA, we were looking at probably somewhere between 5 and maybe 10, 15 years.
Okay. So even without the tax credit, it still makes sense, because obviously buildings should be there a lot longer than the 5 or 10 years.
I mean, there's other things that are happening. Carbon tax is coming down now pretty fast, and I think that's going to start to hit developers and residential building owners within the next year or two. 2024 is when it's supposed to start, and it's only going to increase. So you cannot install gas-fired boilers now in New York City. There's just been a moratorium that says you can't. All gas cookers are going to be banned. Not new installations. This is, I think it's 2025. So using gas-fired boilers is becoming sort of definitely not the way to go. In fact, in New York City, there's a shortage of gas, so a lot of the developers are now having to look at alternatives.
Right, but obviously, not every part of the United States is like New York City, and that what I was trying to get at, that even if you take out the tax credit, even if you take out all the upcoming regulations that may or may not happen, and you talk about a return within 5 to 10 years, which is a lot shorter than the duration of your building. So it only makes sense as you start thinking about it. Yeah. Let's take a step back. Say that people have assumed that yes, this is the way to go. Are there regulations? Are there standards out how to design an energy foundation?
Yeah, there are recommended guides, I would say, is more the kind of what it is. So, I mean, I was part of a group of probably again 10, 12 years ago to the UK's Ground Source Heat Pump Association. So there is an Energy Foundation guide. We've just completed writing an International Ground Source Heat Pump Association version. That's going through sort of internal review at the moment. That will be issued, I think, probably by the end of the year out to the general public for comment. It will include a whole myriad of geothermal solutions, and what we've managed to do is include heat and energy foundations into that guide, which is a good step forward. So it's kind of trying to raise the profile of this type of solution.
But there are right now, as far as you're aware, no specific American standards that cover this topic.
Well, there's guides for drilling boreholes and geothermal loops in general.
Okay.
But none specifically saying, for energy foundations. Only good guidance, which was kind of built out of the all the kind of experience that we had in the UK with the 60-odd, 70-odd projects that we completed over there.
Yeah. Another aspect that comes back time and time again, and it has to do, I see a lot of parallels with foundation design in general. Generally speaking, when we design a foundation and we then do testing on the foundation, we find out that the capacity of the foundation is a lot higher than what we originally designed for, what we expected. Same thing with when you have an energy foundation. You already gave one example where the amount of energy that was generated by that system was a lot higher than what was originally designed for or was assumed. Is that something that is a general trend, or is there anecdotal evidence? Are there more case studies there? How do you personally see that the amount of safety that is in there? And I'm asking that because a lot of people are saying, yeah, people like yourself, you will promote an energy foundation. It's all pie in the sky. You say it's fantastic, but once it's built, the results are a lot less than what was originally envisaged.
So yeah, I mean, and again, the energy model is a crucial piece of the design process for a geothermal system, any geothermal system, and providing that long-term management and monitoring is also a key part. I mean, we could all kind of put together an energy model and work out, well, what do we think the amount of heating and cooling is going to be? Traditionally, gas-fired boilers, rooftop chillers have been designed. Okay, so what's the peak heating and cooling load of this building? Okay, let's double it or triple it. Let's add N+1 resilience. That's the size of the equipment that needs to go in that building. With the geothermal system, it's a lot more detailed. We need to understand what's going on every hour, and it's become common that energy modeling will provide that level of detail. So 8,760 hours a year. The important thing is that you can strip out any simultaneous heating and cooling that's happening together, and in a ground source heat pump system, you can deliver that without any additional equipment. So yeah, I mean, which makes sense. It's basically a no-brainer.
But generally speaking, it's not that once those systems have been put in and once the model has been developed, that the final outcome is less.
Well, yeah. So what's going to be interesting, and what I'm keen to do is on the 561 Greenwich project, We've got quite a few universities tied into the data that's coming out of the foundations there. One of the things we're going to be able to see is, okay, what is the true energy model that's coming out of 561 Greenwich? How accurate was the mechanical engineer in assessing, the heating and cooling requirements for that building? I'm confident that what you're going to see. We said we're going to deliver 38% of the heating and 32% of the cooling, I think it was. I reckon that we're going to see those figures probably double. It's human nature to err on the side of caution, even with foundations. Okay, factors of safety. It will have been done on the heating and cooling loads to make sure, that there's adequate heating and cooling capable there. So I'm really, and as soon as we get that information, I'm determined that we're going to make it public what the true information is on that side. So as part of the slides that you've just seen, hopefully 18 months from now, we'll be able to see a true picture of what that energy model is, what the true heating and cooling load is. We know what we can get from the foundations. And like I said, I think we can do more heating. So it's about playing around with the ground loop and trying to drive and deliver more heat and cooling from the ground source than using an air source heat pump. That's where the true OPEX savings come from, is that making the system run, the ground source run longer than the air source heat pump. Actually,
right. Another point of criticism or an argument why not to do this whole thing is that you've been talking about the Inflation Reduction Act, giving grants for this whole thing, but that may not last forever. Then you've also been talking a lot about New York, where obviously you do a lot of your work. And the answer is then, or the argument is then that, well, listen, New York is New York, but there are other parts of the United States. Is it, in your experience, that you need to have a certain type of climate, a certain type of temperatures, or can we apply energy foundations as easily in New York as we could it in California, as we can it in Florida, Texas, or wherever? How do you see that?
Absolutely. And all those locations, energy foundations will work. What we're going to find is there's more cooling and less heating in each of those. It's working out what we do with most buildings, interestingly, will be cooling dominant. So it's about how we deal with the heat, and heat is going to be becoming an increasing issue over time. So it's about providing heating to hot water. So is there an opportunity to heat swimming pools? Is there an opportunity to provide heating generally to hot water in some way? The other way, and again in northern climes, would be to utilize and provide a snowmelt capability on sort of surrounding sort of sidewalks, footpaths, and maybe roadways, ramps into the basement car park, that kind of stuff.
Yep.
And you can utilize, rather than just wasting that heat into the atmosphere, you can store it and reuse it when you need it, rather than just rejecting it to atmosphere.
So basically, the bottom line is we can apply this solution throughout the United States. It's not location limited. If you look at the OPEX and the CAPEX, the total financial picture, we're not dependent on grants to make this thing work. It makes sense anyhow. It doesn't affect your foundation that much from a structural point of view or geotechnical point of view. Then the final question that I have, where can people find reference material, books, brochures? Can we put something on the sustainability website or sustainability committee website? How can people learn more other than just watching this webinar and listen or talking to you or calling you or getting involved with the sustainability committee, where we have this energy foundation work group where we try to promote this anyhow?
Yeah, I can provide all those links, no problem at all. And I'm sure, I thought we had there's a database within the DFI that had links to all that information. The Ground Source Heat Pump Association, the UK Ground Source Heat Pump Association. There's I think you have to pay for the guide these days, but if you put if you search in your search engine Ground Source Heat Pump Association, energy foundations, you should come up. You should find that there's a section in there where you can locate and buy the guide. It's a really good guide. It was written by a group of Fleur Leverage from Leeds University. She's done a lot of conductivity testing in foundation piles. Duncan Nicholson from Arabs, and a whole multitude of other kind of consultants in the UK at the time. The IXPA guide will be out later this year. I'm keen that we circulate it to the DFI and get their comments back on it too.
Yeah, and then issued as a DFI endorsed document as well.
Yeah.
Tony, thank you very much. For the attendees, I hope that this kind of got your interest. Obviously, you were interested in energy foundations anyhow, otherwise you would not watch this. But it shows that energy foundations, it's not the perfect solution. That there is no such thing as the perfect solution for everything, but at least it's something that you should consider, and that we should start thinking about it much more frequently than we actually do. If you're interested in this topic more in general, as I mentioned already, the Sustainability Committee has a work group dealing with energy foundations. So join the Sustainability Committee. We can make you part of that work group and get you involved in that way. And finally, if there are any additional questions, either contact Tony or myself or the DFI office, and they'll forward those questions. We're more than happy to answer those questions. I want to thank you for being here. I want to thank Tony, of course, for being our presenter and main speaker here today. And I think there's... Sorry? I hear some feedback. And there may be, if you signed up for this thing in a certain way, you can either get PDHs, presumably. There you are, to page registrants. And then if you are interested in other webinars, let DFI know, or let me know. DFI obviously is producing quite a few different types of webinars. Personally, I'm heavily involved in the It's Money webinars that are being held every other month to indicate and illustrate how increased testing saves money. But as a Sustainability Committee, we also have webinars. This one, I already told you earlier about one that we did about a year ago, where the executives of American companies indicated why sustainability makes sense. Last year, we did a webinar on the carbon calculator that I briefly mentioned today. And later this year, we will have another webinar in September where we take practical problems when you apply the carbon calculator. And we have Katie Costello from Isherwood presenting that webinar. So that's on September the 12th in this year. I hope to see you there. And like you said, please feel free to join the Sustainability Committee to learn more about energy foundations. And with that, thank you very much for being here. And I look forward to seeing you in the next webinar in the near future. Thank you very much.